In the previous video, we have discussed enterprise integration challenges like networks are unreliable, networks are slow, no two applications are same, and change is inevitable. Applications change over time. So enterprise integration developers over time overcome these challenges with four main approaches. Like I said, no two applications are same. Let's take a .NET application and a Java application to be integrated. The first approach is file transfer. In the file transfer approach, the applications need to agree upon the file format and who will write the file and who will read the file and who will delete the file. And the second approach is shared database. In this approach, the two applications will have a shared physical database, and one application will write the data to the database and the other application will read the data from the database and vice versa. And there will be no duplicate data in the database, so there is no need for sending the data to other applications from one application. They can rely on the database to get the data without having to communicate with other applications directly. The next approach is RPC, remote procedure call or remote procedure invocation. In this case, one application will expose its functionality in the form of web service or an API, and whatever application is interested in invoking this functionality will make a call to this web service or API, and this communication is synchronous and real time. And the last approach is messaging. In messaging, both these applications will be connected via a message channel, and both the applications need to agree upon the message format, and one application can send message on this channel and other application can subscribe to that channel to receive the messages. In this case, the communication is asynchronous, and this message sender can send the message on the channel and go on to finish its other tasks without waiting or without wasting time on whether the other application will receive the message or not. Essentially, all these four main approaches in enterprise integration solve the same problem, but based on the situation, business requirements, and other considerations, we can utilize all these four approaches in a single integration solutions, or a combination of two or three approaches based upon um, the advantages and disadvantages each approach will offer. We will stop and I'll continue. In the previous session, we have uncovered the four main approaches in enterprise integration. And in this session, we will try to uncover messaging, which is one of the enterprise integration approach, in more detail. What is messaging? In a telephone system, if I wanted to call someone and the receiver has to be available to take my call at the same time. But what if the other person whom I'm calling is not available at that point in time? Then we have an option to send a voicemail, and that voicemail will be queued in the receiver's voicemail box. And when he is back and available to take or receive the messages, he will receive the message that I have sent. And this communication happens asynchronously. So messaging is about sending the message from one application or one computer to another computer, and not worrying about whether the receiver received the message or not. What is a messaging system? Let's compare messaging system with a database system. Database system's responsibility is to save or store the data which is persisted by the application in a reliable fashion, and make it available for any application who is interested in reading the data from that database. Similarly, messaging system is about sending messages from one computer to another computer, or one program to another rather other program, in a reliable fashion, where the sender can send the data or the message without worrying too much about how that message is delivered to the receiver, or whether the receiver will receive the message at all. So to do that, we have messaging system. Like there are different software vendors who provide database systems. We have different software vendors providing message-oriented middleware softwares. And these systems are responsible to receive the data from the sender and send it to the receiver in a reliable fashion. So what is a message? Message will have two parts in it. One is header and another is the body of the message. Header of the message will have the metadata, like who is sending it, where it has to go, and things like that. And the body of the message will have the actual message which is sent by an application or a computer to another computer, another application. So when the enterprise integration developers talk about message, they generally refer to the body of the message And most of the cases, the applications do not need the message header information, and message header information is mostly used by the messaging system. How, from where it is coming and where it should go and how it should be sent, and some additional properties. For example, if the requirement is to persist the message and make sure it is delivered to the receiver, and if the receiver is not available, make it persistent and deliver at a later point in time and things like that. So header of the message will be used by the messaging system, and the body of the message will be used by the applications which are trying to communicate in an integration solution. Having said that, now let's see what are the steps in message transmission. Here I have shown the diagram, multiple steps involved in it. Primarily, there are 5 steps in the message transmission. You can see this is a sending application and this is a receiving application. These two applications are taking part in the enterprise integration solution using the messaging approach. And in the sending app, we have first step is to create the message. And this symbol denotes the data, the actual data, and it is packaged in a message, which is the message header plus the body of the message. And the symbol denotes the message storage. It can be in memory or persisted to disk. And the second step is to send. And this is the messaging channel, which is actually part of the messaging system. And sending the sending application will send the data to the message channel, and the mess and the sending application can go on to the other tasks without worrying too much about whether this message will be sent to the receiving app or whether it should wait until the receiving app receives the message and sends an acknowledgement. It's the responsibility is now transferred to the messaging system, and it's messaging system which should reliably send the message to the receiving app. And the third step is deliver from the sending app to the receiving app. And the fourth step is to receive the message in the receiving app. And the fifth step is to uh, take the data from the message and process it for further uh, business requirements, whatever data is present in that message. And here, these are the two important concepts. One concept is about send and forget. The second concept is store and forward. The send and forget is the concept which is followed by the app, and store and forward is the concept which is followed by the messaging system. Send and forget is about the sending app, sending the message to the message channel and forget about it and go on to other works. Basically, this is how the asynchronous communication happens. And it's messaging system's responsibility. In other words, when we compare the messaging system with the database system, when an application sends data to the database, it's database system responsibility to store that data reliably, and whenever any other application need that data, it should be able to provide that data whenever other application queries that database. So the similar way, the messaging system, it's messaging system's responsibility to reliably send the message from one application to another application. So in order to make it reliable, messaging system follows this store and forward. Before, in step two, before sending the application to the receiving app, it tries to store the message here and then forwards it. Uh, we may feel that these are like too many overheads, but in enterprise integration, sending data from one computer to another computer, and like we discussed in the previous sessions, the networks are unreliable. We do not know if the receiving application is available to receive the message, and even if the sending app and receiving apps are available to communicate at that point in time, we do not know if the networks are reliable. So just to make this messaging system more reliable without worrying too much about data loss, we have to store and forward in every possible step so that the messaging system could retain the message in any failure situations. And in step three, after it delivers, as soon as it received at the receiving app, it stores it again. And then it will forward the message to the receiving app, and then from there it is uh, processed further. I'll stop here and continue. In last session, we have seen what is messaging and what is messaging system. And in this session, we will try to uncover why use messaging in enterprise integration solutions. As with any sophisticated solution, there is no one simple answer, but the quick answer is messaging is more immediate than file transfer, better encapsulated than shared database, and more reliable than remote procedure invocation. However, those are just the beginning of the advantages when we use messaging. More specific benefits include remote communication. As we discussed in the earlier sessions, integration is about connecting different computer systems which are oftentimes continents apart and make them communicate and transfer data between them through networks, and messaging enables them to communicate with each other, and it requires data to be copied from one computer to another computer, which is a lot more complicated, and messaging makes this data serializable by converting it into byte stream data and transfer the data between these computers via networks. And next advantage is platform and language integration. In enterprise integration, we will have to integrate different systems which use different languages, different technologies, and different platforms. And perhaps that is because these applications were developed over time by different integration teams. And integration have to integrate these divergent applications. And oftentimes, these applications have to communicate with the lowest common denominator, such as flat files with obscure formats. And messaging enables them to connect to the messaging system, and each computer or each system or each application with different language or platform or technology will interface with the messaging system to transfer data between the other applications which are taking part in that integration solution. The next advantage is synchronous communication. With remote procedure calls, the caller or the sender has to wait for the receiver to receive the message and process and send back a response or an acknowledgement, which will have different downsides or disadvantages. Whereas messaging enables asynchronous communication, and in case of asynchronous communication, the sender do not have to wait until the receiver receives the message and process it. It doesn't even have to wait until the messaging system delivers the message to the receiver. It will only have to wait until data is sent to the messaging system, and the messaging system stores the message in the messaging channel. Then the sender can go on to perform other works instead of waiting for the response or a reply from the receiver. And the receiver, when it processed the message and wanted to send an acknowledgement or send a response back to the sender or the caller, then it can send via different message, another message. And the sender, the caller or the sender has to handle those responses or acknowledgements using callback mechanism. The next advantage is variable timing. With synchronous communication and remote procedure invocation, when caller calls the receiver, it has to wait until the response or acknowledgement is sent back to the caller. And in this way, the caller can only process as many messages as the receiver can process in a given time. Whereas in asynchronous communication, the caller do not have to wait for the response or acknowledgement from the receiver. So caller can batch request the receiver and perform the other tasks without waiting for the receiver, and the receiver can send back, process those messages at its own pace and send back the response or acknowledgement using callback mechanism. And the next advantage of using messaging is throttling. In synchronous communication and remote procedure invocations, oftentimes the receiver can receive too many calls at the same time, which makes the receiver to crash and have performance degradation issues. Whereas using messaging, the receiver can handle or control the flow of the message in incoming messages, and at the rate at which it can process without having any performance degradation. And the caller do not have to wait for the response or acknowledgement from the receiver, causing it to block all the threads it can process and also have performance degradation on the caller end. So messaging allows asynchronous communication and do not cause any performance degradation. And the next advantage of messaging is the messaging uses store and forward approach that we have discussed in the last session, which means that the messaging system will store the message before it forwards to the receiver. And when the receiver or the network has any issues or receiver is not available to take the message from the sender, then the messaging system's responsibility to retry until it succeeds. And since the message is stored already, sometimes in memory and sometimes to a disk when we have an option to choose a guaranteed delivery, the store and forward approach uh, makes it more reliable than in synchronous communication or in remote procedure invocation, where the sender just forwards or moves the message from the sender to the receiver, and if there are any network failures or the receiver is not available, then the message is lost. And messaging system or messaging enables reliable communication without worrying too much about data loss. And the next advantage is a disconnected operation. And what this meant is there are certain business situations where some applications are designed deliberately to operate in a disconnected fashion. And when the system or application is available to connect to the other applications or the other systems, then the messages should not be lost during the disconnected operation. And when it reconnects to the network, it should process all the pending messages which are queued when it was operating in disconnected operation. For example, these applications range from applications which are deployed on PDAs, laptops, and automobile dashboards, or any operations personal's devices. They go onto the field to do some operations, and when they work on the field, they try to log their work into those devices. And the device, when it comes back to the enterprise and connects with the other systems in the enterprise, the messages that are queued inside during the work day of the operations personnel will be processed later in that day, or things like that. And messaging system also acts as a mediation layer. In other words, if we build an enterprise integration solution where there are multiple applications which are connected, not just like 10, 15 systems, maybe hundreds or thousands of applications in an enterprise application. And for example, if I have an application and I got disconnected from the network for some unforeseen situations, when the network is available again, I do not need to connect back to all the applications that are present in the enterprise integration solutions. I just need to connect with the messaging system, and messaging system will make sure I'm connected with all the different applications which I intend to connect with and communicate. And the last but not the least advantage is thread management. In case of remote procedure invocation or remote procedure calls, if there are too many calls on the receiver and the receiver is not able to handle or process the messages that are incoming, and all the threads will be blocked by the parallel jobs or messages that are received and on the receiver end, which will make it difficult to manage the parallel threads. Whereas messaging with asynchronous communication, the caller do not have to block the thread un- until it receives a message or response or acknowledgement back from the receiver. Instead, it will close that thread and go on to other work, while receiver can take its own time to process the message, and whenever the acknowledgement or response is ready to send it back to the caller, it will open a new thread and send the response or acknowledgement back to the caller. This way the thread management will be uh, optimal in case of messaging when compared to other integration approaches, like in case of remote procedure invocation, which are synchronous and real time. There is no place for delays in the communication if we opt for that kind of approach. I'll stop here and continue. In the last session, we have uncovered why use messaging in enterprise integration solutions. There are several different reasons why an application or an enterprise could benefit from messaging. Some of these reasons are technical details which application developers most readily relate to, whereas others are strategic decisions which resonate best with the enterprise architects. Which reason is more important to you depends on the integration problem that you're solving. There are all good reasons to consider messaging and take advantage of in your enterprise integration solutions. Having said that, in this session, we will try to uncover some of the challenges of asynchronous messaging. Asynchronous messaging is not a remedy for all your integration problems. I'm sure it can solve many of the challenges integrating disparate systems in an elegant fashion, but also it introduces some new challenges. Some of these challenges are inherent to the synchronous messaging model, whereas others are specific to the messaging system that's being used. The first challenge is application developers need to adapt new programming model called event-driven model and asynchronous messaging. What that means is event-driven model is different from traditional monolithic procedural application programming model where application logic is coded in a single main method and there are some other helper methods which it calls, and the coding is easier, debugging is easier, and the execution path is uh, linear. Whereas on the other hand, modern event-driven model, the application logic is spread across different event handlers, which will be triggered by the incoming events, messages, or triggers. The application logic cannot be coded in a single main method. It's spread across different event handlers, and these event handlers will respond to the incoming messages. This makes the coding a lot more complex than the procedural programming model. And a simple application a method needs a request queue, reply queue, an error queue, and a correlation identifier, and an invalid message queue just to start with. This definitely solves the problem of scalability and responsiveness, but adds more complexity to the coding and the application developers have to deal with. The second challenge is sequencing issues. Messaging utilizes send and forget approach. It is sure that the message will be delivered, but we are not sure when it will be delivered, and this raises a new problem or, or sequencing issues in the messaging. And if your system needs the message to be in the sequence, then there is an additional overhead and add some more logic. And in utilizing the correlation identifiers, you have to resequence the messages, because messaging system will not have the control on the sequence of the message, what it delivers. And the next challenge is synchronous scenarios. With messaging, most of the systems are designed in asynchronous fashion, and not all systems that you design will have a send and forget approach and can wait until the message response is delivered. For example, consider an application where user is trying to check the airline ticket price, and he need to see the ticket price right away, not after some undetermined time. And for these scenarios, the messaging systems have to place some application logic to deal with the synchronous messaging and send the response to the user right away. The next challenge is performance. Messaging definitely adds overhead to performance. Taking the data, creating a message, and sending and processing it adds a lot of overhead, and it could definitely have performance issues. And there are certain situations where there are two existing systems which would like to synchronize, and there will be a huge chunk of data, and dividing that huge chunk of data into gazillion small units would not be a smart idea. If we have to synchronize to existing systems, instead of using messaging, and ETL, extract, transform, and load tools are more appropriate in the initial phase where the systems synchronizes, and after synchronizing, then the messaging can be utilized to keep them in sync going forward. But to begin with, messaging could be performance, could add performance issues if we have to synchronize to existing systems. The next challenge is a limited platform support. Not all messaging systems proprietary protocols support on all the systems which we need to integrate. Some of the times, sometimes just FTPing a file to another system is a lot easier, or lot more supported than the messaging system, which will have some proprietary protocols. And the next challenge is vendor lock-in. Once you decide to use messaging, you have to finalize on the messaging system and which vendor's messaging system you would adopt. And once you lock into that vendor, it's difficult to change the messaging system, and not all proprietary messaging systems support all your application systems that are to be integrated. So this is another challenge with asynchronous messaging or messaging model. So when you have to solve some integration problems, you have to keep these consequences in your mind before you come to a conclusion to use certain messaging system. I would stop here and continue. Messaging is an asynchronous technology which retries delivery of a message until it gets successful. In contrast, most of the applications use synchronous calls to call a sub-procedure or a remote procedure call. Here are the call semantics for a synchronous call and an asynchronous call. In synchronous call, the process A is the calling process which calls the process B, which is the sub-process or a sub-procedure, and the process A is blocked until it receives a response or an acknowledgement back from process B and continues to process after it receives the response or the results from process B. On the other hand, asynchronous communication uses send and forget approach. In this case, process A sends a message to process B and forgets and continues to process the other messages which process A has to process. And when process B processes this message and sends an acknowledgement, it uses a callback mechanism, and this can greatly improve the performance, but there are certain implications which we have to keep in mind. And the first implication is there is no more single thread communication happening. So when process A is executing, it sends a message to process B, then the process B executes or processes that message in another thread. So there are multiple threads. So this will make the debugging much more difficult when compared to asynchronous calls. The second implication is the process A sends a message to process B, and when process B sends an acknowledgement or sends a response from process B to process A, the process A should have some context in which that message is sent, and it should be able to correlate that message response with the original request that is sent. So this needs an additional thinking and designing implications to be kept in mind. Another implication or uh, or a trade-off when using asynchronous communication is the order in which the message gets processed is not uh, sequenced, which means that it executes in any order. When process A sends a message to process B and goes on to another work, then process B takes that message and starts processing it. And meanwhile, process A can send message 2 to process B and 3 and 4 and so on and so forth. So process B will execute in any order and not necessarily in the order it receives the message from process A. And this also adds to the complexity when designing asynchronous solutions. In this session, we will try to uncover the most common integration scenarios like information portals, data replication, shared business functions, service-oriented architecture, a distributed business process, business-to-business integration. This list by no means is the complete list for all things integration, but these are the most common scenarios we may come across in enterprise integration. The first integration scenario is the information portals where many business users need to access several different systems or applications to answer a question or a customer query. Like the customer care representative have to check the order status placed by the customer. For the customer care representative to check this order status, he may have to access different applications like order management system or uh, the web order application where it takes the online orders, and some other miscellaneous applications like shipping management systems or uh, inventory management systems. For the user to avoid having access to all of these systems, we build an information portal and integrate all the backend systems with this integration information portal and provide the order status in a visually uh, designed application for customer care representative just to query the order status and get all the information that is needed. The second integration scenario is data replication. Imagine a situation where a customer is calling to the customer care representative to update his address, and this customer's address might be there in several different systems like customer care system or a billing system to send the invoice, or the accounting system where it calculates the tax, or the shipping management system where it creates the label to send or ship the order, and things like those applications. So the customer will call and tell the customer care representative to update the address, and the customer care representative will update the address in the customer care system. However, the other systems should also have the updated address. So in these scenarios, we will go for an integration approach called data replication, which will uh, use any of the mechanism to get the data from the customer care database in this case and update in the other databases like accounting or shipping or billing and things like that. And there can be two approaches. One approach is ETL, extract, transform, and load. The other approach is MOM, message-oriented middleware. And which approach to follow will be specific to the situation or the problem that is present in an enterprise. And next, in a most commonly used integration scenario is a shared business function. So, like we may have to replicate data, we also may have to use some redundant functionality. For example, if we have to uh, check whether the SSN presented by the customer is valid or not. So this is a common scenario in that enterprise, and it will be used for multiple different purposes by different systems. Then this redundant functionality should be implemented once and should be exposed as a function which can be used by different applications or systems within that organization or enterprise. And this also raises a doubt whether to use a function or replicate the data. So it totally depends on that particular system whether it should maintain a redundant copy of the data in that application or system itself, or it can rely on an external function inside of an enterprise. So we have to put two things in mind. We have to keep two things in mind: the amount of control, which is limited if we are depending on a shared function, and shared function can also be intrusive. So there should be some security involved in accessing these shared functions. Whereas in the database, if we have to replicate the data in a database, we have to see what is the rate of change. For example, customer address will not change that frequently. So we have to keep rate of change also in mind when we have to choose the data replication integration scenario or the shared database function scenario. And the next integration scenario is service-oriented architecture. In this approach, we will have several different functions implemented, and these functions are integrated in a service bus architecture, and all these functions are exposed as services. And the service bus will have the service directory, what all services are available in that service bus. And these services should also have the service contracts, and this service bus can be integrated with any application. Just in this case example, order management system, and the order management system can access any of the service available in this service bus uh, by making compliant calls to these different services. The next approach is a distributed business process. Uh, Most of the business scenarios, to fulfill a task, for example, placing an order is a task, which is a simple daily based task for an enterprise, will need several different systems to be integrated to complete or fulfill or place the order. For that, instead of uh, exposing all the services available inside of an enterprise, we create a process management component which will take care of interacting with different types of functions available to complete the task of placing the order. So in these scenarios, we will implement a PMC, which is process management component, and expose it to the user to place the order, and other functionalities which are necessary to fulfill the task will be taken care by the PMC by interacting with the other functions available in that enterprise. And the last integration scenario, but not the least, is business to business integration. So far, we have seen all the different integration scenarios, which are mostly within an organization or within an enterprise, but we can use integration to integrate business to business applications as well. Consider a shipping company which ships the customer products, will need to calculate the shipping cost, or will need to calculate the tax related, or if it is overseas, then the customs related activities. So shipping company do not necessarily implement its own application or a system to calculate the cost of shipping, or the tax, or the overseas customs duty and things like that. There are several different trading partners which are ideally providing these services to shipping companies. Then the shipping companies can be integrated with these trading partners, and this is one of another most common business to business integration scenarios. I would stop here. In this session, we will try to uncover application integration criteria. Enterprise integration is the task of making separate applications work together to produce a unified set of functionality. Some of these applications may be custom developed in-house, while others are bought from third-party vendors. These applications probably run on multiple computers, which represents multiple platforms and may be geographically dispersed. Some of these applications run outside of the enterprise by business partners or customers. Some applications which need to be integrated might not be even designed for integration, and they cannot be changed. These are some of the issues what makes integration difficult. So what makes for a good application integration? If the integration needs are always the same, then there will be only one integration style. But like any complex technological effort, application integration involves a range of considerations and consequences that should be taken into account for any integration opportunity. So what are the application integration criteria? The first criterion is application integration itself. If you can develop a single standalone application which doesn't need to collaborate with any other applications, then you can avoid the whole integration issue entirely. Realistically speaking, any simple enterprise will have multiple applications. The applications need to collaborate with other applications to provide a unified experience for its employees, customers, or business partners. And what are the other main decision criteria for application integration? The second criterion is application coupling. Even integrated applications should minimize dependencies on other applications, which allows the other applications to evolve without causing any issues to the other applications in the integrated solution. Tightly coupled applications make numerous assumptions about how other applications work, and when these applications change and break those assumptions, integration breaks. The interface for implementing integration solution should be specific enough to produce a useful functionality, but general enough to change as needed without causing issues for the other applications. The next criterion is integration simplicity. In an enterprise, developers should strive to minimize the changes to the application which needs to be integrated, and also minimize the amount of integration code when designing an integrated solution. Yet changes and new code will usually be necessary to produce a good integration functionality. And the approaches which minimizes the impact on the applications might not be a good integrated solution. The next criterion is integration technology. Integration techniques require varying amounts of software and hardware, which are expensive and leads to vendor lock-in. And also it adds burden to the developers to learn these integration tools to use these to integrate different applications. The next criterion is data format. Integrated applications should agree upon a data format or should have an intermediate translator if the applications insist on different data formats. The related issue is data extensibility and evolution, how the data changes over time and how it will impact the applications in that integrated solution. The next criterion is data timeliness. Applications often tend to share data among other applications in an integrated solution. So we have to consider the length of time between one application to another application when the data is shared. The latency in the data can cause other complex problems in an integrated solution, like the data can become stale, and developers should strive to share the data in small chunks rather than waiting for large chunks of data and sending across to the other applications. By then, the data can become stale, which leads to more complex integration issues. The next criterion is data or functionality. Oftentimes, integrated applications do not just want to share data, but also share the functionality. Each application can invoke functionality in another application remotely, and the remote invocation might look same like local functionality invocation, but will have other network related or latency related issues when we have to invoke some functionality which are remotely separated in the networks. The last criterion is asynchronicity. Computer processing is generally synchronous, and when a procedure wanted to share data or call a subprocedure, the assumption is the subprocedure is available all the time. But if the subprocedures are remotely located, then the communication should happen between these two applications over a network. So at times the networks are unreliable, our networks are not available. So in those scenarios, it's better for the calling procedure to operate asynchronously. By asynchronous, I mean we have to invoke the subprocedure, and the main procedure will not wait until the subprocedure is executed. The main procedure will call or make a log request and go on to the other work, confident that the remote procedure will handle the request in the background asynchronously. So these are some of the application integration criteria. Now the question becomes, which integration approach will better address the integration criteria which we have to handle. We will try to uncover in the coming session which integration approach will best suit which criteria we discussed here. I'll stop here. In this session, we will try to uncover messaging systems concepts. In the enterprise integration styles, we have discussed various options of connecting applications with one another, which includes messaging. Messaging makes the applications loosely coupled by communicating asynchronously, and which also makes the communication more reliable because the two applications do not need to be running at the same time. Messaging makes the messaging system responsible for transferring the data, and the applications do not really worry so much about how to send the data, but focus on what data that it need to share with the other application. Like most technologies, messaging involves certain concepts. The first concept is channels. Channels in a messaging system is like a virtual pipe which is connected um, which is connected between the sender and the receiver, and this channel is responsible for sending the message data from the sender's application or computer to the receiver's application or computer. When we install a messaging system, these channels will not be available uh, by default out of the box. It's the developer's responsibility to decide what channels would be needed for their integration to send the data between the sender and the receiver. And the next concept is a message. Message is an atomic packet of data which a sender application intends to send the data to the receiver, and it has to uh, divide the data into small packets, wrap it as a message, and send it over a channel so the receiver will receive it. The next concept is multi-step delivery. Uh, in the simplest form, a sender will send a message to a receiver, but in real time, there might be some additional steps that might be needed between the sender and the receiver. For example, if the sender is sending a message and there should be some filter in between, or transformation is required, or any format change is required, and receiver is expecting in a different format than the sender is sending, then those kind of steps are executed between the sender and receiver by different application components, which we will dig more deeper in the coming sessions. But generally, we call them as pipes and filters. The next concept is routing. In large enterprises, we will see numerous applications connecting with numerous different channels, sending messages uh, to different various applications. So, how a sender and the intended receiver will make sure that the right data is received. That is uh, based on routing. So routing is an intermediate step where it will create pipes and filters in between the sender and receiver in a large enterprise. And at times, one sender has to send the data to different multiple receivers. So routing is a messaging concept which will be responsible for routing the messages to the right destinations and to the right channels and to the right receivers. And sometimes the original sender might not even know which channel will take that message to the final receiver, and at times the sender even doesn't know who is the destination or the message consumer, what that sender is sending. And the next concept is transformation. Like we discussed before, if the sender is sending a message and it's in a format, say for example X, and the receiver has to receive the message not in the format what sender sends, but maybe in a different format, let's say Y.
then we should have some additional messaging components between the sender and the receiver, which will transform the X message to a Y message and send it to the receiver. This will make sure that the sender and receiver are decoupled, and also they are not overburdened by transforming the message. For example, one sender is having multiple receivers. One receiver expects it in Y format, and some receiver expects in Z format, and some receiver expects in W format. Then sender cannot transform each and every message for different receivers and send it over. Instead, there will be intermediate components which will be taking care of transformation, and this way the sender can only focus on sending the data in X format, and the translators can take care of whatever transformation is required in between the sender and the receiver. And the next concept is endpoints. Endpoints, uh, like we discussed before, sender application do not need to know how to integrate with the messaging system. Likewise, the receiver also do not need to know how to integrate with the messaging system to receive the data. Instead, there will be some bridged code, or maybe we can call it as integration code, which will apparently know how a sender application works, and how a receiver application works, and how a messaging system works. And this integration code is responsible for connecting the sender and the messaging system, and likewise the messaging system and the receiver, so that the integration will become seamless. And here in this simplest diagram, this is how a sender will send a message to a receiver, and the message will look like this. It will have a header, and it will have a body of a message, and header of the message is metadata, which is usually used by the messaging system, which includes what is the origin of that message and what is the destination of that message, and other necessary filter information which is needed for the messaging system to route that message to the right receiver. And body is usually ignored by the messaging system. Body is something which sender sends, and it is transferred or transmitted to the receiver as is without altering anything in the messaging system. And the receiver doesn't really focus on the header of the message, but it usually needs the data which is inside the body of the message for it to extract and process it further. But the sender and receiver, like we discussed, will not directly be connected. It needs a messaging system, something like this, which is installed separately in an enterprise. And we will discuss different messaging systems vendors available maybe in the coming sessions. But a messaging system will look like this, which will have the channels like this. And these channels will not come right out of the box when we install this messaging system. It's like I said, it's the developer's responsibility, who is trying to integrate the sender application and the receiver application, what kind of data they wanted to transmit between these two applications, and what kind of channel it might need. And this is a virtual pipe which will be connected from the messaging system to the sender application, and on the other side, it is connected to the receiver application. I would stop here and maybe dig more deeper into this messaging concepts in the coming sessions.
In the last session, we have uncovered some of the core messaging systems concepts, and in this session, we will dig deeper into one of the core concept called message channel and try to explore what types of channels are available and what is the decision criteria to create these channels and who is responsible for creating these channels. Is it the application team or the owner of the messaging systems or the messaging systems team? The first theme for creating these channels is the number of channels or the fixed set of channels. Basically, when two applications decide to exchange data from one application to another, it will be using a channel. And when we install a messaging system onto the environment or the enterprise where we have to integrate the applications, the channels will not be readily available. So it's on to the developers who will be integrating the applications, what sort of data they are trying to share between those applications, what is the data type of those data, and they have to know how many channels might be necessary. So these are all things which should be decided at the design time, not at the runtime. Sure, there will be some message channels that will be or that can be created at the runtime dynamically, but most of the channels that might be necessary for the applications to exchange data should be decided at the design time and agree upon a format, what sort of message data they will be sending across that channel. So there will be a fixed set of channels which should be created at the design time, and the application teams have to make use of those channels when developing these integrations in an enterprise. The next uh, theme or the challenge is determining the set of channels which might be necessary for integrating the applications, whether it should be decided by the messaging systems teams or the app teams. Basically, when we start a fresh integration, uh, in the most cases, it will be the application team who will be deciding how many channels might be necessary and what kind of data types those channels would be carrying. And these details should be shared with the messaging systems team for them to create these channels for them. And the initial set of applications, once they are integrated, then when there is a new application which is willing to participate in that integration, then we have to do an analysis if that application will share the functionality with other applications which are already present in that integration solution. Then it might be necessarily use the existing message channels, and if there is any new functionality which is added into that integration, then certainly there might be new channels that might be needed, which will be shared with the messaging systems again. And this kind of iterative approach is followed until the enterprise integration is completed and seamless. And the next theme we should focus on is the direction of these channels. Basically, the channels are uh, not unidirectional or bidirectional, and they do not have any direction. We can just think about a channel as a bucket where some app will put the data in and some application will take the data out of that bucket. So there is no direction. Only it's when one application sends a data and other application receives the data, then the direction comes into picture. And usually or technically, the channel can be bidirectional, meaning that the application send data to that channel and the same application can consume the data from the same channel. But in reality, uh, it's technically possible, but in reality, if the application sends the data to that channel and also consumes the data from that channel, then there is a chance that the application consumes its own data instead of consuming the data which is sent on that channel by different application. For all good reasons, these channels are kept unidirectional, meaning that one application can send the data but not consume from the same channel, and the other application can receive the data, but again, that cannot send the data on that channel. So it's unidirectional, and the consequence is if those two applications would like to participate in a conversation, then there might be an additional channel that is necessary for the receiver to send back some kind of acknowledgement to the uh, sending application. So this is the downside, but this downside is for all good reasons, not to mess up the entire integration layer. And the next uh, topic I would like to discuss is the channel decisions. So, how do we decide which kind of channel to use? For example, should we use one-to-one channel or one-to-many channel? When I say one-to-one channel, it's a point-to-point channel, which is essentially a JMS queue. And if we choose one-to-many, then it's publish subscribe channel, which is essentially a JMS topic. And there are also certain channels which are readily available in the messaging systems when we install these messaging systems right out of the box, like invalid message or dead letter channel. We will come to this in a while. Let's go back to one-to-one. So imagine a situation where your enterprise handles incoming orders for some shopping related application. So you will be receiving orders on a channel and you have to process those orders. So this is the business case scenario, and obviously you wanted to process one order only once. So in this case, it's appropriate to go for a one-to-one or a point-to-point channel, which will consume the incoming orders like here. order 1, order 2, order 3 on this channel, and the receiver will receive these orders in the same sequence, order 1, order 2, order 3, unless we have some parallel processing or multiple receivers to process or multiple receivers to handle the incoming volume. It will be processed in sequence. And this will essentially make sure that one order is only processed once. Now, let's compare it with the one-to-many or publish-subscribe channel. For example, in the same enterprise, there is a business use case where you have a customer in your database, or you maintain a customer related data, and the customer wish to update his address. His address will be essentially in different applications, be it billing or be it invoice or tax related stuff or be it customer care. So there are three different applications which will be having the customer address, and the customer will not send an address change request or a message three times. Or say, for example, you have 10 systems which will be having his address. He will not send the address update 10 times. He will only say that, hey, I have an address change, so I'm sending this change request. So he will send one message, which is address change. And in this scenario, you can opt for publish subscribe channel, where you will publish one address change, and on the publish subscribe channel, you have multiple receivers for the same message. And this address change will go a copy of each message, a copy of that message, each message coming on the publish subscribe channel will be sent over to each receiver, so that all the systems that are present will have the updated address. So based on the business use case, we can go for a publish subscribe channel or a point-to-point channel. And all this is depending upon the app teams, or it's all app teams responsibility when designing what kind of channel to pick for certain functionality. We will dig more deeper into the other types. Okay, I forgot to cover an invalid message or a dead letter channel. For example, in ideal case, when we create a channel, um, the expectation is that the sender will only send a valid message on that channel. But in real-time situations, there will be cases where sender might send some invalid data message or invalid or maybe not all mandatory fields are present in that message. So it's quite possible that sender will be sending some invalid messages, but the receiver will have some expectation on that particular message, that the receiver only processes uh, validated messages and or rejects all the invalid data messages. So where those messages should be delivered. So most of the messaging systems will have by default some of the channels which are for these reasons. Invalid message channel, which hold all the invalid messages on that channel, and hoping that some other monitoring application or some tool will be taking care of those invalid messages on a timely in a timely fashion. And the next one is a dead letter queue. Sometimes not only invalid, but also some weird messages which are not even uh, in line with the receiver's expectations will also be ending up on the channels. So those kind of messages will go to the dead letter channels. So these are some inbuilt
or right out of the box channels which are available from different messaging system. The last topic I would like to cover is crash proof or guaranteed delivery. In general, message channel uh, will only have the messages in its memory. So when any crash or any shutdown for any maintenance of the messaging system happens, then when the messaging system is back online, the channel will not hold the messages which were previously present. And if your application or based on the business criticality, if you think that we need to get back all those messages which were present before the downtime or crash, then you have to opt for guaranteed delivery, which is a mechanism where the messaging system persists all the messages to a disk, physical disk, before it is delivered to the receiver, and receiver acknowledge that that message is received. And if the receiver is not responding, or for any network failures, or for any crash reasons, or any downtime, then the messages are stored on the disk. And when the systems are back online, those messages from the disk will be uh, put on the channel again for the processing. So this is definitely a performance overhead on all the systems, but you have to see the trade-offs. You have to compare if the performance degradation is uh, okay and message loss is not okay, then you have to go for a guaranteed delivery uh, option. With this, I'll stop here and continue.
In this session, we will try to uncover message routing in more detail. We are going to cover around 10 message routing patterns that are available, which are essentially useful for providing routing and brokering abilities to any enterprise integration solution. The first message routing pattern is content-based router. As the name suggests, this router will examine each individual message, and based on the content of the message, it will be routed to the right recipient or right receiver. So this is a diagram which essentially explains all the available message patterns in a single uh, process flow. And the content-based router is a simple message router which processes one message at a time, and it is a stateless message routing pattern. And a single message will come out of the a router, and exactly one receiver will be receiving when a content-based router is used. The next pattern is message filter, which is also a simple messaging routing feature which processes one message at a time, and a single message is out. However, based on the filter conditions, whether that message will be sent to the end receiver or not. So it filters out any messages that are not matching the message filter that is defined. And the next router is a dynamic router, which is essentially a content-based router, but a content-based router, we have to specify the conditions in the design phase Whereas in dynamic router, we have an additional component which we can use to control the flow. And based on the runtime uh, situations, we can direct the router to various different receivers, which is not static, which are dynamically created at runtime. The next message router is recipient list, which is essentially a list of receivers we define beforehand at the design time, and all the receivers or recipients in that list will be receiving the message. However, we can also control using a control component, and this recipient list can be updated at runtime based on certain conditions, and the recipient list can be changed. So this is again a simple message routing pattern, process one message at a time, and multiple messages will come out. And for recipient list, a parallel processing occurs, and the receivers which are listed in the recipient list will be receiving a copy of the message. The next pattern is a splitter pattern. Um, Imagine in your enterprise, you receive bulk orders, say, for example, 1,000 orders per message. Then there might be a situation where you have to split all those 1,000 orders and process each single order. And then this is the pattern, messaging router pattern, which we will be using to split all the 1,000 incoming orders and process them sequentially. And this is the message pattern we can make use of, which is a splitter. And the next pattern is somewhat related to the pattern which we discussed right now, which is splitter. This is an aggregator. So once you process all the 1,000 orders, then you have to aggregate all the processed orders and send it to some downstream destinations. Then this is the pattern that is useful to aggregate all the multiple orders into single message and send to the downstream consumers for further processing. So here, this flow process multiple messages at a time, which are also stateful. Basically, you have to maintain the state. In other words, you have to know somehow that there are 1,000 orders that should be aggregated and send it to the downstream system. So for that same reason, aggregator message router is a stateful message routing pattern. Then the next pattern is resequencer. For example, the 1,000 orders that you have processed might be processed in parallel. And when parallel processing is in place, there is no control on the sequence of the orders. Some components or apps may be faster for different reasons. Uh, those processes or those orders will be processed faster than other process, which is processing essentially at a lower speed. So this will make all the orders uh, run out of sequence. And if there is a requirement in your business that you have to send the orders in sequence to the downstream consumers, then you might be looking at a messaging pattern called resequencer. And this pattern is again stateful because you have to maintain the state whether you have received all the orders and whether you have resequenced all the orders in the same order as it received. In aggregator, at times there might be some invalid orders which will be not processed by the process components. So most of the cases, the aggregator will be receiving less messages out, maybe out of 1,000 orders. If some 10 orders are invalid, then aggregator would receive 990 orders. Whereas in resequencer, it is essential that it should get the same number of messages out. So when we resequence after 990 successful order processings, it also should get all the 10 invalid orders explaining why they are invalid. Maybe certain mandatory fields are missing in those orders, like uh, the shipping address is missing, or billing information is missing. Any possible invalid message would be resequenced and also explain why that message is not, or why that order is not processed. So far, the patterns which we have covered are simple message routing patterns. In other words, one single message router pattern is involved, whereas few next message routers which we are going to discuss are composed message routing patterns. In other words, it might necessarily use one or more message routing patterns to get more complex message routing requirements in a business fulfilled. And this is the composed message routing patterns. And let us first see parallel processing message routing patterns. And the first one is a composed message routing pattern. For example, if you have a bulk order or a bulk message and you have to process each individual message, then you have to use a splitter, something like this. Then, and if you have to route the messages to different receivers downstream, then you may have to use a content-based router, something like this. So it can include a splitter and a content-based router, which is essentially a composed message processor. Not necessarily the same splitter and content-based router. It can use multiple simple message routing patterns in one single complex message routing pattern. Then it's a composed message processor. The next composed pattern is scatter gather. In the scatter gather, which is basically a splitter, then an aggregator, and if needed, a resequencer. So once you receive a bulk message which have multiple individual messages, you will first split them, scatter them, and send it to different message or process components for any further processing. Then once the processing is complete, then you have to gather all the messages back and send to downstream uh, consumers. That's about scatter gather. And the next composed message pattern is routing slip. Routing slip is essentially a predetermined linear list of components which a message should follow, which is essentially defined at the design time. So if you go to any government office or driver's license office, when you go to the front desk, you will have uh, certain people you need to meet. Go to the next counter to take a picture of you, go to the next counter to submit your documents, and go to the next counter to submit your old driver's license, and then finally go to the counter where you will be issued a new driver's license. So similarly, in enterprise integration, a message might need to go to several different components to successfully get processed and go to the downstream consumers. Then a routing slip will maintain a list of components which should be which a message should follow. And in those situations, we will use a routing slip pattern, which is essentially a sequential, predetermined linear flow. The next message routing pattern is process manager. Process manager is something similar to routing slip. However, you do not know which process component a message should follow beforehand, meaning that at design time, you do not know or you cannot determine what processes it should follow because the incoming message is so different from one another. Uh, the each message should follow different processes or go to different processes for the processing. And that only can be determined during runtime. And in those situations, you have to go for a process manager, and the process flow is not linear or predetermined. It can take any path. And this is a classic example of enterprise integration pattern where a process manager is designed and developed, and there will be several different conditions in the flows where certain conditions are executed, and if it passes the condition, then go to this flow. If it is passing another condition, then go to this flow. And there will be always an otherwise flow where none of the conditions is matched and you have to take certain flows. So this is essentially a central process manager where decision will be taken during runtime based on the content of the message. The last pattern is message broker. For some technical glitch, I couldn't complete the recording of my previous session. So in this session, I'll continue from where I left in my previous session and uncover what is a message broker, and I would like to quickly run through all the message router patterns which we have discussed in the last session. Content-based router routes the messages based on the contents of the message, and message filter is something either it sends the message to the receiver or do not send it based on the filter condition. And dynamic router is something same as a content based router, but if we cannot decide at the design time what content to be examined in a message, then dynamic router with some control component can be routed at runtime and send the messages to the downstream consumers. Recipient list is again a list of components which we predefine in a list, and the message will be sent to those recipients. And this also can be controlled using a control component at runtime and uh, update or add or delete uh, a component from the recipient's list based on runtime conditions. And the next router is a splitter. If you get a bulk message with multiple individual messages, then splitter is a messaging routing pattern which will be useful to split all the individual messages and send it to the downstream consumers. Then aggregator, once you split all the messages and process them individually, and if there is a business case where you have to aggregate all of them and send it to the downstream as a single message, then you have to use an aggregator. And aggregator is stateful because you have to maintain the state and you have to see if all the messages that were uh, received or processed or not. And the next pattern or a message routing pattern is resequencer. And if the business demands that you have to process the messages in the same order it received, then a resequencer might be useful to resequence all the processed messages, because in aggregator, if you choose to do parallel processing, then you do not have the control on the sequence of the flow or sequence of the messages. Then you have to resequence them using a resequencer, which is again a stateful component. You have to maintain the state to see if you have received all the messages that were processed or not. And these are all the simple message routing patterns. Then we have composed message routers. The first one is composed message processor, which is essentially two or more simple message routing patterns used in in a complex message routing solution. For example, you split the messages if you get a bulk order and then process them. Then again, you have to send or route the individual messages to different downstream consumers. Then you have to use a content-based router. And if you have to aggregate them again, you have to use an aggregator. So based on the business complexity and the requirements, you may have to use two or more simple message routers, which comes under composed message processor. Then comes the scatter gather, which is again a bulk message which will be splitted or scattered into individual messages and sent to different receivers. And then again, at the end, you have to gather all the messages that were processed and sent to the downstream consumer. That is a scatter gather. Then routing slip. A routing slip is something which is a list of components where you will be sending the message to all those list of components. And process manager is something which is similar to routing slip, but routing slip is predefined, predetermined, linear, whereas process manager is dynamic and it doesn't need to follow a linear path. So with all these message routing patterns, at times your integration solution may become like this with so many point-to-point channels, and it can easily become an integration spaghetti, which is really hard to maintain and hard for the new team members to understand. And for this reason, if the point-to-point channels are growing in large numbers, you have to look for a message pattern called message broker, which is a hub and spoke model, which will essentially have a hub where all the message processing happens, and based on the conditions met, it will be routed to different apps which are like spokes. I'll stop here.
In this video, I'm going to talk about enterprise integration challenges. Enterprise applications rarely live in isolation. Whether your sales application must interface with your inventory application, your procurement application must interact with your order management application, enterprise applications tend to perform better when they are integrated with other applications within an organization. However, all integration solutions have to deal with certain fundamental challenges. The first challenge is networks are unreliable. Integration solutions have to transfer data from one computer to another computer across networks. Compared to a process running on a single computer, distributed computing has to be prepared to deal with a much larger set of possible problems. Oftentimes, two systems to be integrated are continents apart, and data has to travel between them through phone lines, LAN segments, routers, switches, physical networks, and satellite links, etc. Each of these steps add delays or interruptions, making networks unreliable. The second challenge is networks are slow. Sending data across networks is multiple orders of magnitude slower than making a local method call. Designing a widely distributed application or a system the same way you would tackle a single application could have disastrous performance implications. The third challenge is no two systems are same. Integration solutions have to transmit data between applications which use different programming languages, different operating platforms, and different data formats. Integration solutions have to be able to interface with all these disparate applications. The fourth challenge is change is inevitable. Applications change over time. Integration solutions could get easily caught in the avalanche effect of these changes, making other applications in an integrated solution impacted. Integration solutions have to minimize these dependencies from one application to another application using loose coupling between these applications, making integration solutions more reliable. I'll continue